Now the other property. Let us go for nitration. See, alkanes on heating with the vapors of nitric acid at about 400 to 450 degrees centigrade. See, this nitric acid can be taken for convenience this way. In fact, a hydrogen free radical is replaced by NO2 free radical. So we get RNO2 and water. Let me give you some examples. If we take methane, we get nitromethane. If ethane is considered, we get the regular product nitroethane. But the interesting point is, because of the cleavage of the bond between two carbon atoms, we also get nitromethane. See, this nitromethane is because of the cleavage of carbon-carbon bond. This is a regular one. Now, when we go for propane, we'll have more options here. Now, these two which are in the same environment give us this product. Okay, 1-nitropropane. Then, if the second one is considered, we get this product. That is 2-nitropropane. Right. Now, these are the regular products. But because of the carbon-carbon bond cleavage, even here also we get different types of products along with these. You can expect nitroethane, nitromethane. Now, these two are due to carbon-carbon bond cleavage. Okay. Right. So that is about nitration. With methane, it is simple, but with ethane, propane, and the other alkanes, it will be little different. You get a regular product. Along with the regular product, you also get products due to bond cleavage. then it's sulfonation. See, in this, a hydrogen free radical is replaced by sulfonic free radical, sulfonic group. Let's see. Alkane with fuming sulfuric acid. What is fuming sulfuric acid? It is nothing but sulfuric acid containing extra sulfur triaxide. It is also known as oleum. H2S2O7. Pyrosulfuric acid. Now, for a convenience, let us write sulfuric acid in this way. You can do this and you get alkane sulfonic acid. Okay. Along with that, we get water. Now, here the interesting point is alkanes containing 6 or more carbon atoms can only be sulfonated. So that is an important. Alkanes having 6 or more carbon atoms. And of course, lower branch alkanes. Only the lower branch, not lower unbranched. Can be sulfonated. Let me give you an example. Taking simple hexane. Hexane on sulfonation gives hexane sulfonic acid. And water. So the point to be noted here is only those having 6 or more carbon atoms can be sulfonated. Then it's isomerization. See, isomerization is a process in which the straight chain isomers are converted into branched chain isomers on heating with anhydrous aluminum chloride and HCl. Let me give you that. even in this also, with alkanes having more carbon atoms, it will be much more interesting. The basic one, if N-butane is taken, it is converted into isobutane. If you take say N-heptane, you get a highly branched heptane called tryptane with maximum number of branches. A very important thing, tryptane, a highly branched one. Okay. Then if N-octane is taken, look at this. Now with N-octane, we get isooctane. Look at this. So this is a special compound. Even with regard to its IUPAC name also, it is so special. Remember the IUPAC name of isooctane. Okay, the IUPAC name of this is, look at 2,2,4 trimethyl pentane. It is the most stable isomer. Okay, this is about isomerization, in which a straight chain alkane is converted into branched chain. The next one is aromatization. See, aromatization actually involves two things. One is a cyclization, followed by dehydrogenation, removal of hydrogen. Cyclization, dehydrogenation. See, aromatization is also known as hydroforming or catalytic reforming. Hydroforming, catalytic reforming. Okay, in this, a regular alkane is converted into its corresponding aromatic compound. Let me take some examples. Consider N-hexane. Okay. Using chromic oxide and aluminium oxide at 600 degrees centigrade, we get benzene, a preparation method of benzene. N-hexane on aromatization gives benzene. See the formula of N-hexane. Let me show you the steps involved. First step is the cyclization. Now, two hydrogens are removed to get cyclohexane. During cyclization, we get this. Now this undergoes dehydrogenation. You can just remove two hydrogens from these two carbons. You get a bond in between them. Then these two. Then these two. That is how you get benzene. Now, consider N-octane. This is little interesting. Look at this. Now what do we get? See, in this case, we get ethylbenzene. I'll tell you how, but let me first write the product. Ethylbenzene, or even this also. This is called ardoxylene, dimethylbenzene. I'll tell you how. Very interesting. Now consider 8 carbon atoms. Possibility number 1. Let me say this. Let us take this. Now, how do we get the first one? Yes. Clubbing these two and taking this as the side chain. We get ethylbenzene. Coming to the second one. Hope you understood. Come on, take the same 8. Different possibilities. Now, in this case, we can consider these two. Now, those attached have got substituents. These two, which have been attached and of course got connected, have substituents, that is a methyl group. So that is how you get 1, 2 dimethyl benzene or orthoxylene, right? If suppose you consider this, look at, if this is considered, we get metaxylene. Now here in this, we got 4 carbon atoms. Consider the first one getting connected to this. Be little cautious. Okay. Now you are left with these two. Now this one is connected, let us say, to the first carbon. Now this is the second carbon. Then this is the third carbon. To the third carbon, you got a methyl group. So what do we get? A metaxylene. Attached to first and third. Of course, different possibilities are there. Okay, so this is how we can write the product. Let me take one more. See if we consider this. Okay. Now connect. See, you got 3 CH2s. You are going to connect the first one to which this methyl group is attached. Now, see, this is the first carbon. I mean, this is the thing attached to the first carbon. This will be the second carbon. This will be the third carbon, and this will be the fourth carbon to which a methyl group is attached. So, we got methyl groups at first and fourth carbon. These are very interesting. Here we got paraxylene. Okay. Yes. Now let us go for combustion. We know that combustion is burning completely in oxygen. General combustion equation of a hydrocarbon can be written as CXHY plus X plus Y by 4 O2 gives rise to XCO2 plus Y by 2 H2. All combustion reactions are exothermic. Large amount of heat is liberated. Now, if the same thing is applied to alkane, it becomes this. In this case, X is N and Y is 2N plus 2, or 2 of N plus 1. On substituting, we get this thing. Okay, so this is combustion, nothing but burning completely in oxygen. Let us see the stability of alkane. You know the stability of alkane is inversely proportional to heat of combustion. Greater the heat of combustion, lesser is the stability of the alkane. I have some one or two things to discuss. See, higher homologs have greater heat of combustion. That means as the number of carbon atoms increases, even heat of combustion also increases. Okay. If you consider isomers, in case of isomers, you know the branched isomer will generally have a lower heat of combustion. Let me give you an example. Consider the isomers of pentane. This is N-pentane with the maximum stability with the maximum heat of combustion, so lesser stability. Now the branching begins. This is isopentane. Then the neopentane. So this is neopentane with more branch. More branching, lesser heat of combustion. Lesser heat of combustion, greater is the stability. So when you go for order of heat of combustion, it will be N iso then neo. Therefore, the order of stability will be exactly opposite, right? Neopentane has least heat of combustion, so is most stable. Then let us consider some cycloalkanes. See, in case of cycloalkanes, more strained ring. I mean the one with the lesser bond angle has higher heat of combustion. Higher heat of combustion per CH2 unit. Let us take this example, starting with cyclopropane. See, in cyclopropane, the ring is maximum strained because here the bond angle is only 60 degrees. Most strained. Okay, then go for cyclobutane with a bond angle of 90 degrees. Then cyclopentane, and finally cyclohexane. Okay, so a more strained one or the one that has lesser bond angle will have higher heat of combustion. Higher heat of combustion, so is least stable. Okay. Now let us go for partial oxidation. The combustion is burning completely in oxygen. But in partial oxidation, it's incomplete. Coming to the first one, a very important one. Say this one has a 3-degree hydrogen. Now this on oxidation using alkaline KMnO4, which provides a nascent oxygen, you get an alcohol. Then two simple oxidations. Methane and oxidation with the copper at a 250 degrees centigrade. gives methyl alcohol. The same thing with a different catalyst. Molybdenum oxide at 350 to 500 degrees centigrade gives formaldehyde. Okay. So this is partial oxidation, incomplete oxidation. Okay.